Hey guys, welcome back. We are going to do the sections for 6.2. So that would be these three examples would help you review section 6.2, transforming and combining random variables. So you should try to do these on your own with your notes and then watch the video. Okay, so give this one a try. Put me on pause and then unrecord or unpause. Okay, welcome back. Here we go. We have a probability distribution, right? So let's just make sure there was a little problem there with their chart. So it looks like the probability of getting 0 is 0.3, and here's my probabilities that correlate with the values. There's a carnival game where tossing a ball into a number of baskets with the goal of having your ball land in a high numbered basket. The probability distribution below is X is this value of the basket on a random selected toss. It tells us that our expected value is 1.1 and a standard deviation is 0.0943. So previous section, we had to calculate these, and so now they're given to us. So it says, suppose it costs $2 to play. Well, I'm going to call that -2, right? Because that's $2 you don't have anymore. And you earn $1.50 for each point you earn on your toss. Okay. So that is if you land in the basket labeled 2, you'll earn $3. So we need to define Y as the amount of profit you'd make on that toss. Okay, so let's just think about one example. So just for example, let's play this example out. If I played the game, I lose $2, but if I land on 2, I earn $3. So the net amount of profit would be I'm making $1, okay? So I have to work that out for each scenario. So I have my Y, right? And then my probability of Y. So it looks like my probabilities here are the same, right? These are my outcomes, but Y is a different variable based on X. Okay, so we figured out for when the value was 2 that we made $1, right? How did we get $1? It was we paid $2 and we earned $3 because it's $1.50 per point. So obviously, if we have 0, we lose $2, okay? If we land on 1, we lose $2, but we make $1.50, so we're really just up, or we're down 50 cents still, okay? And then the last scenario, we lose the $2 because we had to pay to play, but if we got 3 points, then that'd be up $4.50. Right? And so then I'm just looking back here on my notes. So that would be $2.50, right? Yeah. Okay. So this is looking good. We have our setup, and they'd said, describe the shape, center, and spread of this probability distribution in the context. Okay, well, I need to make my probability distribution chart. So this is my probability. And this is my Y, and my Y is my profit from game. Right? And I'm either going to lose $2, lose 50 cents, gain $1, or gain $2.50. Those are my only possible outcomes. So what are the probabilities of those? So 1, 2, 3, 4, 0.1, 0.2, 0.3, and 0.4 are my possibles. Okay, so this one goes up to 3, right? This one goes up to 4. I'm going to make $1 20% of the time and make $2.50 only 10% of the time. So this is my distribution of my data. So I can describe my center, shape, and spread, right? So shape Notice my shape didn't change. This is the same shape of that data. So how would I describe the shape of that data? I would say, let's see what I wrote. I worked these problems out earlier. It looks like it's unimodal. It looks, slightly skewed to the right. So you could say slightly skewed right. And that would be fine. So what is my measure of center? Well, here in this chapter, we've been calculating the mean. So what is the mean of y? Well, we can calculate that, right? This times this, plus this times this, plus this times this, plus this times this, right? And what is my spread? Well, the measure of spread we've been using is our standard deviation. And so if I have to do both, I'm not going to do the calculator. I'm just going to use my technology like I used before. So back to my technology. Where was that? Did I really go off of that website? I really did. Wow. Okay. Probability distribution calculator. Here it is again. And what are my values? I have a possibility of losing $2. Losing 50 cents, making $1, and making $2.50. And what is the probabilities of that? Well, 30% I will do the first outcome, 40% of the time I'll do the second outcome, 20, and then 10%. So let's find the mean first. And it looks like our mean is, I didn't hit approximation. So I could say that's negative 35. Seven divided by 20. All right, I'm going to go back. Let's go back. -2. So losing 35 cents. Yeah, and that's what I had said before in that fraction. So it's not a game that's going to be very profitable, right? On average, but that's how you make money. If you work for a casino, you have to make sure that the mean is a loss for the people playing so that you can make money. So we still need the spread. So going back, we can do this again, but find the standard deviation. It's not liking that. All right, I calculated this before, so just trust me. The standard deviation is 1.4145. Now, could we have used something in class to make this faster? So this is based on our calculations, but could we have used something in class to make this faster? And the answer is yes. Because what did I do here? Essentially, I just took my, how did I get from X to Y, right? I took this and whatever that was, so if it was 2 points, I multiplied by the $1.50 per point, right, in my example. And so I could have done this faster by saying, well, whatever y is just $1.50 times x. Well, the same would have been true for mu. So if we take mu and take $1.50 times x, right? But then remember, I also had this $2. So it was take away $2. So this was my income, right? But then I had to subtract off the $2 to play. So you would have to subtract off the $2 to play, and this should work out nicely, right? So if I would have done that, I wouldn't have had to do the full calculation. I would have just taken 150, and mu x was provided. And so this would have given me the same answer. I would expect to lose in the long run 35 cents on the gain. Now with standard deviation, how is this affected when looks like I'm multiplying by 150 and I'm subtracting? Well, we learned in class it changes when we multiply and divide, but it doesn't change when we add or subtract. So we would take this same 150 and that would affect sigma x, right? So if we do that, 150 times sigma x, 0.0943, we actually get exactly the same measure of spread, even without using the technology. So this question is much faster if you use these observations from class. However, the same is true. We could check this calculation by actually doing out the example. All right. Now, what's next? Okay, so new fact scenario. If Mr. Costello's class is expected to check their homework in groups of 4 at the beginning of class, students must check it as quickly as possible. So each of them are checking it one at a time, right? One right after the other. So if each student checks it, what is the mean and standard deviation of the total time necessary for all 4 students to check their homework? So let's say they all did, and this is helping us. So based on what we just found out, the total should just be adding them up because that should make sense, right? So we can add, right? So whatever the average for Alan and the average for Barb and the average for Corey and the average for Doug, we should be able to add them up. And so this would be, for instance, pretending that just by chance, everybody did get their average time. You're adding up each of these x values to get your total. And that should kind of make logical sense. So if we add these up, we get 3.3 minutes. So it typically takes them 3.3 minutes working together. All of them each have separate fluctuations, but that would be what we should expect for their total time. So what should we expect for their total standard deviation? Well, again, we can't add standard deviation. We can only add variances. So we said in class, we could add variances, and then I'd have to take the square root of their answer. And so that's exactly what we're going to do. So that would be 0.1, 0.4, 0.8, 0.7, and we're going to square each of those and then take the square root of the final answer, which is the square root of 1.3. So on average, we would expect for them to complete it in 3.3 minutes, and that should typically vary from that by about 1.14 minutes. Now suppose Alan and Doug would like to race one another. Again, they have each their own standard deviations and average times. So here's Alan and here's Doug. What are the mean and standard deviation of their differences if we subtract Doug from Alan? Okay, and we have to interpret these values in context, so we can't forget to do that. All right, so the mean, right, of Doug minus, so that would be their difference, right? The mean of their difference should just be mu Doug minus mu Alan. We know we can add and subtract these. So if Doug typically is 1 minute and Alan typically is 1.4 minutes, then it looks like Doug is 0.4 minutes faster on average. Now I will remind you that this you might have to think here. It's kind of a tip. Remember, if Doug is a minute and Alan is 1.4 minutes, we're trying to be faster. So Doug is actually faster. Okay, now what about our standard deviations? How much should we expect their times to differ on average? If we expect Doug to be on average 0.4 faster, but by how much should that number vary? So again, their difference would be, I can't add standard deviations, I can only add variances. So that would be Doug, and the other one would vary. Alan's time would vary. And you would have to add these. We don't subtract them. So that would be the calculation. Doug was 0.7, right? And Alan was 0.1. And so if we combine these, we get... So what is that in the context? So the difference between their times, Doug minus Alan, will vary, typically, by 0.71 minutes from the mean of 0.4 minutes, negative 0.4 minutes. Nice. Okay, last one, right? Yep, that's my last one. Mr. Mosley and Mr. Liberty are avid video game golfers. Both like to compare their times. Mosley's time is normally distributed with a mean of 110 and a standard deviation of 10. Mr. Liberty's is normally distributed with a mean of 100 and a standard deviation of 8. Find the mean and standard deviation of their differences, Mosley minus Liberty, okay? And assuming their times are independent, which would be important there. Okay. So learning what we have learned so far, we know that the mu of Mosley minus Liberty, we could merely subtract. Mu Mosley minus mu Liberty. So if mu Mosley is 110, mu Liberty 100, we're expecting them to vary by 10 minutes, or it just says find it. All right. And then find the standard deviation. And they're not making me calculate. So the standard deviation, Mosley minus Liberty, even though I'm subtracting, I have to find combined variances. So that would be, I'd have to take the square root of that, Mosley and Liberty. So what are their variances? Well, it looks like 10 and 8. So that'd be the square root of 164. Square root of 164 is 12.81 minutes. So we're expecting the difference between their times to be 10 minutes and to typically vary from that by 12.81 minutes. Now, find the probability that Mr. Mosley will finish his game before Mr. Liberty on any given day. Okay, so we know these are normally distributed, and so we would know that this would also be normally distributed. So what is the mean and standard deviation? Well, the mean is this 10 minutes, right? And the standard deviation is 12.81 minutes. So we have our mean and we have our distribution, and we can find the area under the curve, and the area under the curve would be the probability. So if we have a 10 here, right, that's our typical difference. What would be the probability he would finish before Mr. Liberty? So this takes some thinking. If, and I'm just going to plug in some random times here. So they're typically about 10. So let's think through this. So if Mosley's usually 110 and Liberty's usually 100, so that would mean that if you get a difference of 10, Liberty is faster by 10 minutes. So what's the probability? Mosley will finish his game before. So this is Liberty is faster. So at 0, they have the same time. And so if it was -10, that would be Liberty is faster. So I'm looking for the area here. This would be all the times that, so it looks like Liberty is typically faster by 10 minutes. So I'm highlighting the area where Mosley finishes first. And so it is possible for him to finish first. And so this would be all the times where Liberty finishes first. And he should, because he typically is 10 minutes faster. All right, so we have our picture, right? I can put my formula. So my value is 0. Oh, formula. My standard deviation. So my z-score is -0.78. I am to the left. And if I look up in table A, that would give me the probability to be 0.2177. Okay, so 22% of the time. So there's about a 22% chance Mosley finishes before Liberty on any given day. Thanks for joining us, guys.